In this section, we'll be revisiting some of the methods that we use to solve second-order linear differential equations. We did this in Chapter 4, and we will be applying these techniques on nth-order homogeneous differential equations with constant coefficients of the form a sub n times the nth derivative of y plus a n minus 1 times the n minus first derivative of y plus dot 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 plus a naught times y equals 0. Now, we can use a shortcut notation for this by introducing an operator that looks as follows: a sub n times d to the power n plus a sub n minus 1 times d to the power n minus 1 plus dot 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 plus a naught, and this operator acts on y. So we can simplify this differential equation to just L of y equals 0. Now, if we plug in e to the power rx into our operator, what we get is the following. We get a n d to the power n, and then that acts on e to the power rx plus a sub n minus 1 d to the power n minus 1 acting on e to the power rx plus dot 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 plus a1 d e to the power rx plus a naught times e to the power rx. Now, when you take the derivative of e to the power rx, that's again e to the power rx, but an r moves to the front. And then if you take the derivative of that again, then you get an r squared. So all these powers of the differential operator translate into powers of r. So what we get here is that this is a n, and then we have r to the power n, and then e to the power rx for the first term. And then for the second term, we have plus a sub n minus 1, and then times r to the power n minus 1 times e to the power rx. And then we can continue that. And then we get a1 times r e to the power rx. And then finally, the last term is plus a naught, and then e to the power rx. Now, what you see is that all of these terms have an e to the power rx in common, so we can factor that out. So if we factor out the e to the power rx, then what we're left with is the following: a sub n times r to the power n, and then plus a sub n minus 1 times r to the power n minus 1, and then plus A1 times R. And then finally, we have plus A naught. And if we call this a polynomial, which is a polynomial in R, remember all the A sub n's, those are constants. So we can call that P of R, right? This whole polynomial. Then solving the differential equation here, setting this equal to 0 is equivalent with solving P of R equals 0, because this whole expression is 0 only if this is 0, because e to the power rx can never be 0. So that leads to the auxiliary equation that we've seen in chapter 4. So the auxiliary equation in this case is a sub n r to the power n plus a sub n minus 1 times r to the power n minus 1 plus dot 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 plus a1r plus a naught. So what we have to do now, by the way, this is something that I'm only doing here for illustrative purposes, but in general, you would go straight from this differential equation to the auxiliary equation by replacing the nth derivative by r to the power n, the second derivative by r squared, etc. So you do not have to show this on an exam. And what we want to do is we want to solve this or set this P of R equal to 0 to obtain the auxiliary equation. And when we solve this polynomial, setting it equal to 0, we're finding the roots of this polynomial. And so just as in chapter 4, we have several cases. So one of the cases is if the auxiliary equation has n distinct real roots r1 through rn, then the n solutions to the original differential equations are given by y sub 1 equals e to the power r sub 1 times x up to y sub n of x equals e to the power r sub n times x. And the general solution to the homogeneous equation is given by y of x equals c1 times e to the power r sub 1 of times x plus dot 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 plus c sub n times e to the power r sub n times x. So let's apply this to an example. We want to find the general solution to the fourth derivative of y minus y triple prime minus 4y double prime plus 4y prime equals 0. So the first thing we do is we want to find the auxiliary equation. And so for the auxiliary equation, we look at the order of the derivative, and that becomes the power of r. So we have the fourth derivative of y becomes r to the power 4 minus y triple prime, that becomes r cubed, minus 4y double prime becomes minus 4r squared, plus 4y prime, that becomes plus 4r. And because there's no y in this differential equation, we don't have a constant term here. And so we set that equal to 0. Now, when we are solving a higher order algebraic equation like this, we're going to look for factors. And since this has no constant term, we can factor out an r. So we have r times r cubed minus r squared, and then minus 4r plus 4, and that equals 0. So factor out that r, verify that when you distribute that r, that you get the original equation here. So by the zero product rule, we already have one root of this differential equation, namely r equals 0. So now we got to factor this cubic polynomial, and there is a formula, a general formula, cubic formula, but it's not very practical. So the way that we solve this is, so the question is, how does this factor? And what we do there is we pick a few values of r and just see if they work. So it's basically guess and hopefully we get lucky. So some values that you would try are maybe r equals plus or minus 1, plus or minus 2, plus or minus 3, etc. So we're going to try r equals 1 and see if that solves or solves this equation here. So we're going to plug r equals 1 into this equation here. And so we get 1 cubed minus 1 squared minus 4 times 1 plus 4. And then the question is that 0? And you can verify this is 1 minus 1. That gives you 0, minus 4 plus 4 gives you 0. So that checks out. And if r equals 1 is a root, so if r equals 1 is a root, that is equivalent with saying that r minus 1 is a factor. So if r equals 3 turn out to be a root, then r minus 3 is a factor. If r equals negative 5 is a root, then r minus 5 or r plus 5 is a factor. So if that is a factor, we can then use long division. So we take r minus 1 and we're going to divide that into r cubed minus r squared minus 4r plus 4. And so r, we're going to just take a look at the first term here. We're going to look at how many times does r fit into r cubed. Well, that is r squared, because r squared times r equals r cubed. And now we multiply r squared times r minus 1, and we get r cubed minus r squared. And then we subtract that from our equation, and we get 0. Now we bring down the negative 4r, but because this completely canceled out, we also bring down the plus 4 there. And so we're looking now at negative 4r plus 4. And again, we're going to just take a look at that r and see how many times does that fit into negative 4r. And so that is negative 4. And so negative 4 times r minus 1 is negative 4r plus 4. And we're subtracting all of that. And we get 0. So this actually divides evenly, which it should because it's a factor. And so when we now look at our auxiliary equation, we can replace that by the following. So this now is r times r minus 1 times r squared minus 4. And the r squared minus 4, and that we're still setting that equal to 0. And the r squared minus 4, that's a difference of two squares. So this is r times r minus 1 times r minus 2 times r plus 2 equals 0. And that means that the roots of our auxiliary equation are r equals 0, r equals 1, r equals 2, and r equals negative 2. And therefore, our solution for our general solution to our differential equation will now look as follows. C1 e to the power and then 0x plus C2 e to the power 1x plus C3 e to the power 2x plus C4 e to the power negative 2x. So we have 0 here, 1 here, 2 here, and then negative 2 here. And of course, we can clean that up a little bit because e to the power 0x is always 1. So this is C1 plus C2 e to the power x plus C3 e to the power 2x plus C4 e to the power negative 2x. And that is our final answer.